So in the last lecture session, we discussed conformational analysis of Newman projections, assessing both the steric and torsional strain for different conformations. Now what we're going to do, now that we've done an instructor provided example, we're going to apply what we've learned to analyze the conformations and analyze the steric and torsional strain for the conformations of the following molecule. So in this case, you're going to identify the lowest and highest energy conformation across the C3-C4 bond, and I'll label, rather than the C3-C4 bond, let's look at the C2-C3 bond, as that's a much more interesting example. So let's look across the following carbon-carbon bond. I'd like you to identify and draw the lowest and highest energy conformation, and I'd like you to calculate the energy of the lowest and highest energy conformations for this molecule. So I'd like you to contribute and draw out your proposed conformations using the annotate tool, or you can share a photo of your work in the Zoom chat. So we'll spend about 5 minutes on this example. And just to make sure, is everyone comfortable using the annotate tool? I know we've used it in past class sessions. It's found under meeting options. In a little drop-down menu, there'll be an option called annotate, where you can draw structures using your mouse or tablet pen. So I'd like you to draw out your proposed Newman projections for the lowest and highest energy conformation across the carbon-2 and carbon-3 bond. And we'll discuss this example in about 5 minutes, but I'd like to see multiple proposed Newman projections for the lowest and highest energy conformations. And there's plenty of space in the class whiteboard for multiple students to propose their responses. And really don't be shy to draw your proposals, and just make sure to clearly label what you would consider the highest and lowest energy conformation. So the idea is in the right place. But one thing I would like you to consider is attached to carbon 2, we have how many methyl groups? How many methyl groups do we have on carbon 2? Otherwise, the backbone is still there. The backbone looks good. And the logic that you're using, eclipsing your bulkiest substituents, that's good. You just need to make sure that both the methyl groups are accounted for. But don't be shy to keep drawing. We still have 3 to 4 minutes on this example. And let's try to get some proposed highest and lowest energy conformations. So don't be shy to keep using the annotate tool. As the responses I was seeing looked quite reasonable. But I'd like everyone to follow up with their proposed structures and try to draw and label the highest and lowest energy conformation. And there's plenty of space, so don't be shy to draw out your own Newman projection for your proposed highest and lowest energy conformation. As there's plenty of space. And don't be shy if your responses are different from other students. The more responses we have, the more we can have a nuanced discussion and talk about different aspects of this problem-solving process. So we have a proposal for the lowest energy conformation where 2 of our methyl groups are anti to each other. And we have our highest energy conformation where we have our methyl groups eclipsed to each other. Does anyone have another proposal? What does the class think for these responses? Do these look reasonable? Do you agree with these responses for the highest and lowest energy conformation? Or if you have an alternative solution, please draw it out on our class whiteboard and we'll discuss in about another minute to a minute and a half. But I'd like to see a little bit of discussion on these 2 structures. Do these look reasonable to everyone? Does everyone agree with their proposals? Does the amount of steric and torsional strain calculated for each of these structures match the lowest and highest energy conformation for this molecule? Let's try to get some responses in the chat for our discussion. What does everyone think about these examples? Do you agree that the structure in yellow is the highest energy conformation and the structure in green is the lowest energy conformation? So we have some pretty consistent agreement across the class discussion. So let's now clear these drawings and let's discuss the instructor solution. So first and foremost, if we are looking at our molecule, if we're looking down our carbon 2 bond, so just for a refresher, so we have our straight chain alkane, Now we are going to look down. We're going to look down our carbon 2, carbon 3 bond. Okay. And now what we're going to do is we're just going to draw an initial picture of what we see. So we have our 2 methyl groups in front, our hydrogen in the back. Sorry, we have our 2 methyl groups in the front right, our hydrogen in the front left, our 2 hydrogens in the back, and then our methyl group like so. So this is one of our first eclipsed conformations. And as you notice, we have our bulkiest substituents with a 0-degree dihedral angle, which we would expect to be our highest energy conformation. The reason for that is if we add up our HH, our methyl-methyl, and our methyl hydrogen interactions, we have 4, 11, and 6 kilojoules, and that gives us 21 kilojoules of strain. Now, if we wanted to generate our lowest energy conformation, we'd separate our bulkiest substituents with a dihedral angle of 180 degrees. So then I'm going to draw my 2 methyl groups completely anti to each other. In this structure, we only have one interaction, and that is a methyl-methyl gauche interaction, which costs us about 3.8 kilojoules of strain, which would give us our lowest energy conformation. So we have both our highest and lowest energy conformation by looking at our dihedral angle between our bulkiest substituents. So the proposed student responses were perfectly correct and were perfectly reasonable for this problem. Does this example make sense so far? Does this example make sense so far? For our highest energy conformation, you draw your bulkiest substituents eclipsed. For your lowest energy conformation, you draw your bulkiest substituents anti to each other. Now, just for completeness sake, I'm going to showcase some of the intermediate structures as a function of some of the intermediate conformations as a function of dihedral angle. And this just is showcasing and proving to everyone that these highest and lowest energy conformations are in fact the highest and lowest energy conformation. So we've established that the eclipsed conformation with a dihedral angle of 0 has 21 kilojoules of strain. At 60 degrees, we have 2 methyl-methyl gauche interactions. So we have 2 times 3.8 kilojoules, which gives us 7.6 kilojoules of strain. Continuing on with our rotation, with a dihedral angle of 120 degrees, we come across our lowest energy one more step. So at 120 degrees, we come across a second eclipse conformation. In this case, we have a methyl hydrogen a methyl and a hydrogen eclipsing interaction. So this structure also has a total torsional strain penalty of 21 kilojoules of torsional strain. So as we can see, at 0 dihedral angle and 120 dihedral angle, these two structures are, or these two conformations are identical in energy. In other words, these two conformations are degenerate. Does that make sense? Does that make sense? Does everyone see how 120 degrees is a degenerate conformation with the 0 degree eclipsing conformation? Because we have the same interactions between the same substituents. Does that make sense? Any questions on that idea? So let's keep going now. If we continue rotating our back substituents another 60 degrees, we end up with the following conformation. Here we go. So this is our anti-conformation. And in this case, we only have a methyl-methyl gauche interaction, which costs us 3.8 kilojoules. So this anti-conformation, where we have 180 degrees between our bulky substituents, is our lowest energy conformation. Let's keep going with 240 degrees. So let's keep rotating our back substituents. And if we rotate our back substituents another 60 degrees, what type of conformation do we have? Staggered or eclipsed? What do we call this new conformation that we have? Is it staggered or eclipsed? What does everyone think? Staggered or eclipsed after another 60-degree rotation? Eclipsed, exactly right. So in this case, we have 3 methyl hydrogen interactions, which in other words is 3 times 6 kilojoules, which gives us 18 kilojoules of strain. Good, good. Finally, at a dihedral angle of 300 degrees, we have another anti-like conformation. This conformation also is anti-like because we have our bulkiest substituents separated by 180 degrees. And in this case, we only have a methyl-methyl gauche interaction, which costs us 3.8 kilojoules. So as we can see, our dihedral angle of 300 is degenerate, has the same energy as our dihedral angle of 180. So let's showcase that with a different color. So these two Newman projections have the same energy. These two conformations have the same energy. Does everyone see that? How 180 degrees and 300 degrees are degenerate, are identical conformations in terms of energy. Does everyone see that? So there are multiple reasonable answers for drawing the lowest and highest energy conformation for this molecule, because we have multiple degenerate conformations that both have the highest and lowest energy. Does that make sense to everyone? Does this idea make sense? Again, the same principle still remains. Highest energy conformation, your bulky substituents are eclipsed. Lowest energy conformation, your bulky substituents are anti to each other. Does this make sense to everyone? Can I get some feedback in the chat that everyone understands this concept? Okay, so just be on the lookout for degenerate conformations, as they can open the door to multiple possible answers. So as you can see, we have two structures that are tied for the highest energy conformation and two structures that are tied for the lowest energy conformation. Okay, so let's do another example. In this case, I'd like you to analyze the conformations along the carbon A, carbon B bond in epichlorohydrin. So I'd like you to look at and draw Newman projections as a function of dihedral angle. So I'd like you to go through and I'd like you to identify and draw out all the Newman projections from 0 degrees all the way to 300 degrees dihedral angle. And I'd like you in turn to tell me and draw out the highest and lowest energy conformation. So this is an example where I'd want you to apply what you've learned in the previous two problems, and I'd like you to draw out each of the conformations and identify the highest and lowest energy conformations. And we'll give everyone about 7 minutes on this example, but I'd like to see students using the annotate tool as they work through this problem. So that way I can check in and provide feedback as you work through and progress through this problem. Epichlorohydrin is a pretty useful building block, and it contains both an alkyl halide and an epoxide functional group. So first, make a model of epichlorohydrin, and then we can focus on analyzing the conformations of epichlorohydrin along the carbon A, carbon B bond. And you're probably going to notice when you're making this model that epoxides certainly are quite strained, as you're really going to have to manipulate your model kit to get the epoxide ring to form properly. So let's try to get some drawn out Newman projections for this molecule using the annotate tool. And don't be shy to build on what other students have drawn on our class whiteboard. And I'd be happy to provide feedback to any structures proposed on the class whiteboard. And we'll get started momentarily. And we'll get started and discuss this example in about 5 to 6 minutes. So let's try to get a few confirmations drawn and a few contributions drawn using the annotate tool. And then once we have a few structures drawn, we can start to analyze the structures and calculate the total amount of steric and torsional strain in each of these structures. Is everyone comfortable using the annotate tool? Really don't be shy. The annotations are completely anonymous, and they really serve as a building block to help elaborate our discussion. Organic chemistry is discussed by looking at structures and looking at different conformational drawings and depictions of structures. As a result, the annotate tool will be invaluable in our class discussion because it allows you to convey information that's difficult to convey in the chat. So let's try to get a few Newman projections drawn. And you don't even have to label them as highest or lowest energy yet. Just draw out as many Newman projections as you can with different dihedral angles. And then we can analyze those structures to begin to sort them in terms of energy and identify steric and torsional strain in those different conformations. So just to help everyone along with this is what epichlorohydrin, let me flip it around to make it easier for you. This is what epichlorohydrin looks like. If you're looking down, one of your carbon-carbon bonds, this is what you would see for epichlorohydrin. Now, don't freak out just because we have a ring. The only thing that's special about this ring is the fact that it connects our substituents. It connects our substituents together. Other than that, nothing changes when you're writing out your different conformations. Just look at the relative position of each of your substituents, identify the steric and torsional interactions, and then by adding together the penalty associated with the steric and torsional interactions, you can get the total amount of strain in each of your conformations. So, did this model help everyone with their Newman projections? Can I see some Newman projections drawn out for epichlorohydrin? They don't have to be in any particular order to start out with. I just want to see some conformations. And again, I can't stress enough, you're gonna need a model kit. Especially, it's incredibly useful to help develop the skill of visualizing molecules in three-dimensional space. So we're going to keep working on this example, and I'd like to see some structures drawn out. This is exactly the type of example that you'd see not on this first exam, but on the second exam coming up later on in the semester. And if possible, if you could draw the hydrogens on the epichlorohydrin carbon, that would be quite useful. And while one student is annotating, you can also pitch your proposed responses. There's plenty of space here on the whiteboard for students to contribute, and I'd really like to see multiple structures drawn. The more structures we have, the more pieces of this problem that we can fit together, and the more we can come up with some reasonable proposals. So before we assign lowest and highest, let's try to draw out a few of the conformations. Let's try to draw out a few of the conformations for epichlorohydrin. Let's get a pool of possible conformations drawn. And ideally, now that we have one conformation drawn, other students can start modifying and rotating our back carbons to generate different conformations. So what do I mean by that? So initially, we had the following conformation drawn. We have the following conformation drawn. Now we can rotate our back. We can rotate our back carbon bond and rotate our back substituents and generate a new set of conformations, with different dihedral angles. And what I would like everyone to focus on is systematically just rotating 60 degrees at a time. And that will allow you to potentially catch and notice structures that you may not have noticed otherwise. So let's keep drawing out some structures. I'd like some students to help out your classmate with a few other proposed structures, and we'll discuss this example once we have a pool of structures and we have some initially identified lowest and highest energy conformations. And ideally, I'd like to see a few other students helping out your classmate with a few additional proposed structures. Or if you have a question, or if there's any way I can help by showing you the model kit again, just let me know. This is one where I really want you to practice your independent problem solving skills. So I'm here to provide support, but I'd like the class to work together. We already have a few structures drawn. So let's try to fill in the blank with some of our other structures. And I find that the more you contribute and you start drawing out structures using the annotate tool in these class discussions, the more that you're able to work on and tackle problems independently. So I'm going to label some of these drawn structures as these are quite good in terms of capturing the key important Newman projections that we need to consider. what I'd like for people in our class to do, if you're not drawing out a structure, you're more than welcome to draw out a structure. There's still plenty of space on this class whiteboard, but if you're not drawing a structure, I'd like you to start chiming in with the interactions found in each of these structures and the approximate energetic penalty. And just for note, a chlorine methyl Gauss interaction is around 4.3 kilojoules, and a chlorine methyl eclipsed is around 7 to 8 kilojoules. An oxygen chlorine Gauss interaction, it's around 1 kilojoule. And an oxygen chlorine eclipsed interaction is around 2 to 3 kilojoules. So what does everyone think so far? What does everyone think so far? Okay, so now we have a pool of structures to look at, A, B, C, D, and E. Okay, wonderful. So now what I'm going to do now is, and what I'd like us now to do, is I'd like us just to note the interactions found in each of these structures. Let's note the interactions found in each of these structures. Let's build on what our classmates have done so far. So in structure A, what interactions do we have? In structure A, what interactions do we have? What interactions do we have? What type of Gauss interactions? What eclipsing interactions? What do we have? So we have these structures drawn. Let's analyze it. What do we have? What type of interactions do we have in structure A? Do we have any substituents that are bulky that are separated by a 60-degree dihedral angle? Do we have any Gauss interactions at play in structure A? Do we have any Gauss interactions in structure A? Yes, so we have a chlorine, methylene, I'll treat it like a methyl Gauss interaction. That costs us about 4.3 kilojoules. Good. Okay, what about structure B? What about structure B? What interactions do we have? Structure B is pretty high in energy, all things considered. So we have a chlorine ox. Is it Gauss in structure B or eclipsed? Eclipsed. So we have a chlorine oxygen eclipsed. So that costs us about 2 kilojoules. What else? What else? Is it Gauss? Gauss is only when we have the 60-degree separation. And this angle is more than 60 degrees. This angle is 120. But what other eclipsing interactions do we have? What other eclipsing interactions do we see? You're on the right track. Let's just keep looking at this structure. Let's try to get some more. What do we see in terms of eclipsing interactions? Do we see any eclipsing interactions in structure B? We're really close. Once we start, yes, we have a methyl hydrogen eclipsed, and that's about 6 kilojoules. What else? What else do we see? What else do we see circled for our eclipsing interactions? HH, yep, exactly right. That's around 4 kilojoules. So this gives us 12 kilojoules total for structure B. For structure C, okay, what interactions do we have here? What interactions do we have? Let's list them out. What do we have for structure C? So we have a CH3Cl eclipsed. So then that's about 4.3 kilojoules. We have an HH eclipsed, which is 4 kilojoules. We have an oxygen hydrogen eclipsed that we can estimate to be around 2 kilojoules. Okay, so this in turn gives us about 10.3 kilojoules. Okay, so we're starting to get some estimations down. What about for structure D? For structure D, what interactions do we have? What interactions do we have in structure D? What interactions do we have in structure D? We have an oxygen chlorine gauche interaction, which costs us about 1 kilojoule. Okay. Notice as well, we have our methylene group and our chlorine separated by 180 degrees. So structure D would be considered our anti-conformation, while structure C would be our eclipsed conformation. What about in structure E? Let's just finish these off. What interactions do we have in structure E? What interactions do we have in structure E? What do we have in structure E? Looking at each of our substituents. So we have a chlorine hydrogen eclipsed interaction. Okay. Which we would expect to cost us around 4 to 5 kilojoules. Okay. We have an oxygen hydrogen eclipsed interaction, which is around 2 kilojoules. And we have a methyl hydrogen eclipsed interaction, which is around 6 kilojoules. So that gives us a total for structure E of about 13 kilojoules. The oxygen hydrogen is let me just check this really quickly. The methyl chlorine interaction for eclipse should probably be closer to 7. Sorry about that. So that would give us a total around 13 kilojoules, while structure E would be approximately 12 kilojoules. So structures C and E are very close in terms of energy. Okay, so we've done mapping and we've looked at the different conformations. What we're now going to do is I'm going to clear the student drawings. I'm going to draw out our own set of conformations, and we'll provide an instructor solution for this problem. So give me one moment, and what I'm going to do is I'm going to copy this page so that way we can view the student response along with how I, as an instructor, would solve this problem. And so let me copy this page, and then we'll go over and we'll discuss the instructor solution for this problem. So we're going to clear all of the drawings. And now let's discuss this problem. And let's go over the instructor solution for this problem. This was a great class discussion that we've had. So let's now talk about how to approach this type of problem in a systematic manner. And let's summarize our findings from this discussion. So the responses I got were very good. We are hitting exactly the key points I was looking for in this discussion. You could identify staggered and eclipsed conformations. You could draw Newman projections. And most importantly, you're able to calculate the steric and torsional strain associated with each conformation. So let's look at this example, and I'm going to turn on the camera for this. So let's look now, and I'm just going to draw my first draft Newman projection. I'm just going to draw a first draft Newman projection. So I'm going to draw what I see. So I have my chlorine up top, my two hydrogens on the side. I have my methylene up top, my oxygen, on the right-hand side, and my hydrogen on the left-hand side. So this is going to be my 0-degree dihedral angle structure. We have a methyl chlorine eclipsed interaction. And that in turn costs us. So our methyl chlorine eclipsed interaction costs us around 7 to 8 kilojoules. We have an oxygen hydrogen eclipsed interaction, which costs us approximately 1 to 2 kilojoules. And we have a hydrogen-hydrogen eclipsed interaction, which costs us around 4 kilojoules. This in total gives us 14 kilojoules of strain. Now what we're going to do, if you want to approach this in a systematic way, what you're going to do is you're going to systematically and step by step, what you're going to do is you're going to rotate your back substituents by 60 degrees, and you'll draw the next Newman conformation after rotation. So let's look at the 60-degree dihedral angle structure. Let's look at the 60-degree dihedral angle structure. So in this case, we still have our front substituents in the same positions. Now we have our oxygen substituent and our methylene substituent. And we have our hydrogen. Now analyzing the following structure, we see the only interaction we have is a methylene chlorine gauche interaction, which costs us around 4.3 kilojoules. Okay. Let's continue on with rotating our carbon-carbon bond another 60 degrees. In which case, we end up with the 120 degrees structure. And we have, in this case, another eclipsed conformation. In this case, we have an oxygen-hydrogen eclipsing interaction, which costs us around 2 kilojoules. Yes, so the methylene group takes up more space, and as a result, there's a greater amount of strain associated with the eclipsing interaction, because this methylene group is taking up a greater region of space. Does that make sense? Perfect. So just like we discussed, we also have a methyl hydrogen eclipsing interaction, which costs us around 6 kilojoules. And then we have a chlorine hydrogen eclipsing interaction, which costs us, I would estimate it would cost us around 5 kilojoules, a little bit more than a methyl-methyl. So we add this together and this structure has 13 kilojoules worth of strain. We've done all of this in our student group example. So you've all demonstrated this to me when we talked through this example together. I'm just redrawing it, and I'm just showing you that there's a systematic way to draw out every single one of the structures that you're interested in, just by rotating your back substituents 60 degrees each time and then drawing what you see. So we have our front substituents, and now after a 60-degree rotation, we have the following back substituents. So in this case, we have, in terms of the interactions that we have, as we discussed previously, we have a chlorine oxygen gauche interaction, which we would expect to cost us around 1 kilojoule. This structure with a 180-degree dihedral angle between my bulkiest two substituents is the anti-conformation. And that makes sense. It's the lowest energy conformation because we have the greatest separation between our bulkiest substituents. Does this make sense to everyone so far? Does this make sense to everyone so far? Is everyone understanding how I'm drawing each of these structures? Does everyone see how I'm getting each of these structures via 60-degree rotation? So now I'm going to rotate another 60 degrees, and this will give us our 240-degree dihedral angle structure. Let me draw. So we have our chlorine and our two hydrogens in the same place as always. And now we have another eclipsed conformation. This time we have a chlorine oxygen eclipsing interaction, which is around 2 to 3 kilojoules. A hydrogen-hydrogen eclipsing interaction, which is 4 kilojoules. And then a methyl hydrogen eclipsing interaction, which is around 6. And that gives us about 12 kilojoules of strain. So the 120 and 240 degree structures are very close in terms of energy. These are very close in terms of energy. Finally, after one more carbon-carbon bond rotation, we get our 300-degree structure. So again, we draw our front substituents in the same location. We now have our back substituents. And in terms of interactions, we have a chlorine methylene gauche interaction, which we estimated to be around 4.3 kilojoules. And we have a chlorine oxygen gauche interaction, which is around 1 kilojoule, which gives us 5.3 kilojoules total. So this is despite being a staggered conformation, this conformation experiences destabilizing gauche interactions. So if we were to make a plot, of energy as a function of dihedral angle, all we would have to do now is read off from our graph, from our calculated values. So at a dihedral angle of 0, we calculated 14 kilojoules. So let's do 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So at 0, we're around 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So let me put our data point for 0 dihedral angle. Okay, let's now look at 60 degrees, 120, 180, 240, 300. Okay, looking at 60 degrees, we found that it was 4.3. Okay, for 120, we said it was around 13. Okay, for 180, it was close to 1. $240, we said it was 12 kilojoules roughly. And then for 300, we said it was around 5.3. So we have 14, 4, 13, 1, 12, and 5.3 in terms of our energy, our steric and torsional strain as a function of dihedral angle. That would give us a graph that looks something like this. So from this graph, we are able to identify that this conformation with a dihedral angle of 180 degrees, this conformation right here is our anti-conformation, and it's our lowest energy conformation, while structure 14 is our eclipsed, and it's our highest energy. And that occurs at 0 degrees dihedral angle. Does this graph make sense? Does everyone understand where we obtained this graph from? Does everyone see how we obtained this graph and drew this graph? Would everyone feel comfortable if you're given a problem just like this on the exam, making a graph just like this and doing the analysis that I've showed you in this example? You should be pretty comfortable because you actually got almost all of the steps needed to draw this graph done just by having me ask you a few questions. So I'm confident that you all understand this material and that you know how to assess the energy of different conformations. I would recommend looking over the homework and doing a few more examples in your book. But this capstone example for this chapter, I think, went quite well. How does everyone feel? Does anyone have any other questions on this topic? Does anyone have any other questions on this topic? Just to showcase how to make the original model. Okay, that's a really good question. Okay, so let's suppose we have our structure. So I make my model kit, right? So I have my model kit for epichlorohydrin, right? Now, what I do is I find the bond that I want to look down. Does everyone see where my finger's pointing? That's the bond that I want to look down. So what I'm going to do is I'm just going to turn my eye. So like the camera is showing what you'd see from your eye's perspective. And then all I do is I just draw what I see. Everything in front goes in front of the circle. Everything in back goes behind the circle. Does that make sense to you? And if you want to draw a different conformation, all you do is just rotate your carbon-carbon bond. So this is the conformation that I drew for 0 degrees. If I wanted to draw 60 degrees, I just rotate it 60 degrees and draw what I see. Does that make sense? Did that answer your question? Perfect. So, any other questions? So for some of these, you'll have to ballpark estimate the value for your Gauss and eclipsing interactions. To answer this question, we'll see in chapter 4 that there's a table of what are known as A values. And we can use A values to estimate these Gauss and eclipsing interactions. So in the next chapter, there's a table of A values, and you can use them to get a sense of the relative amount of steric and torsional strain for different substituents. Just qualitatively, if I think about like chlorine compared to hydrogen, chlorine is a bit larger. So as a result, I'd expect some larger eclipsing interactions. Does that make sense? So the point is not the exact numbers, unless it is just a hydrocarbon. Because like we know the HH eclipsing interaction, we know that to a very exact value. But for these other eclipsing interactions, your main goal is just to estimate them so you can start to compare the energies of different conformations. And the main criteria you use is how large is the substituent? How much space does the substituent take up? And bulky substituents have larger Gauss and eclipsing interaction energies. They have a greater amount of steric and torsional strain. The A values that we'll see next chapter will allow you to address these unique substituents in a more of a quantitative manner. Does that completely answer your question? Any other questions on this chapter? Any other questions on this problem? These 3 problems that we did on Newman projection analysis, in addition to the other examples in the notes, are ones that you should focus on, as these are your bread and butter questions for this chapter.
Will the graphs always look kind of like cosine graphs, or do they ever?
They will almost always be cyclical in nature, because every 60 degrees you go from a eclipsed to a staggered conformation. Does that make sense? Perfect. So that's all I have for this chapter. So we'll close out